Hello, this is the type of decoder. In this video, I'm going to be talking about some seldomly used keywords.
And also, I want to talk about atomic types. So, we'll see how far I get in here. So, I'm going to do a vector, I'm going to do atomic, I'm going to do thread, I'll have mutex, and I'll throw in chrono just in case. Probably not going to use that. And, wait, what am I doing? Avoid. Okay. First thing I want to do is recreate a race condition from an earlier video. So I'm going to have x starts at 0. I'm going to say I have a for loop, so sti 0 is less than 100,000. That's a million. There we go. sti plus plus. Okay. I'm going to say x plus plus. So that's what each thread will do. Let's say auto fn procedure, I don't know, equals, pass an x to it, then return a void. Okay. Okay. Yeah, I'm going to say for t ci equals 0, ci less than 10, let's say, plus. It's going to run 10 times. And for each one, I'm going to see I have a standard vector of threads, vec threads. I'm going to say vec threads in place back. That lets me call the constructor of a thread, standard thread constructor, like this. But I can just forward the arguments. It's kind of nice. So I'm just going to pass it a fn proc. Yep. And anything else? I'm going to need to join everything. So for, I'm going to say auto reference th. So thread coming from vec threads. th.join. So once all those threads have finished executing, I'm going to say standard cout x, give it the value of x, inline. Okay. Now it's going to have the wrong value because all the threads are trying to read the current value of x and then add to it and then put it back in memory where it was at the same time. So let's do that. And you can see I'm linking here with pthread. So the library I'm including is called pthread. You have to do that. So test. You can see it's not a million. It's a different value each time because of the race condition. Okay. Now before the way we fix that, I'll show it again real quick, is just to do standard mutex, tx. We're also going to reference that mutex in each of these threads. And we can do mtx.lock. We can do mtx.unlock. So every thread has to wait to be able to lock until the other one before it unlocked. And if nothing's locked before it, just lock right away. It'll add and unlock. We'll just keep doing that over and over again. Okay, so it's clear, clear, okay, test. You can see it's a million now, it worked. But there's an easier way to do this that I want to show. So instead of using a standard mutex, what we can use is what's called an atomic. So standard atomic int. So atomic can have any type that is an integer type or a floating point type. And technically it can have any type that is trivially copyable. And I'll kind of show an example of that and why you probably just want to stick with primitives in a second. But for now, I can just use this exactly like an integer. So I'm not going to change any other code. It's not using mutex anymore, it's just atomic. So all I did was add atomic here. So then you can see it worked, just the same. So that's automatically going to wrap the mutex around this object. So one thing I want to say too is with bool, if you do a standard atomic bool, this is going to use a spin lock, whereas this is going to use a mutex. So for bools, it's actually really fast. For things like your integer types, it has to be a bit slower. Aside from integers and floating point variables, you can make something that's trivially copyable also be atomic. It's less useful, but I'm going to show it anyway. So type def struct number, and we'll say number. Okay, we'll give it int x. Okay, so what I want to do here is I want to say I have standard atomic number, and we're going to say n. Now I can't do n.x equals 0. If I try and do that, it's going to complain because the dot operator gives me access to members of the standard atomic object. And it's not going to have a member called x. The struct number does, but this atomic class doesn't. So see, struct standard atomic number has no member x. So what I'm going to do here is I'm going to say instead, if I want, I can grab the entire structure out of there. So number, let's say n2 equals n. So basically, atomically grab the entire number structure out of here and store it in this temporary variable. Now I can say n2.x equals 0. Bad because we're accessing standard atomic tx, which doesn't exist. Come on. There we go. So this will work, and then what we can do is we can say n equals n2. So if you pull the entire structure out in a way that's thread safe, because it's atomic, basically there's a mutex around it, we mess with the values you want, and then we stick it back in, that will work. That is legitimate code. See? It lets that compile. And in fact, I can do the same test I did over here with this, just so you can see. This is going to be really dumb, but let's go ahead and just give that a try. In fact, I need to actually do this over here anyway, just because I need it to start at 0. Yeah, okay, and then I'll do something over here. We're going to say, we'll call this temp, and it's going to be ++. Okay. Now down here, I'm going to do the same thing. I'm going to say n2 equals n atomically, and then we're going to say standard cout n.x, let's say, n2.x. That should work. Should also have a value of 1,000,000. N is not captured. 27. Oh, right, I didn't actually put that in the capture group of this lambda. So I'd have to actually reference it like this. Okay. Okay. Ooh, that didn't work. 227.958. I should be grabbing the entire structure value atomically, incrementing it, and then putting it back in. That's interesting. That should have worked. Future tepid coder here. I'm reading through the specification here on cppreference.com. I'm seeing the primary standard atomic template may be instantiated with any trivially copyable type, T, satisfying both copy constructible and copy assignable. The program is ill-formed if any of the following values is false. Is trivially copyable being false? Is copy constructible? Is move constructible? Is copy assignable? Or is move assignable? So if any of these are false, then it's an ill-formed program. So let's see if I actually made a mistake there in my code with regard to any of these. So I do test.cp. I actually want to test to see if number here fails any of those tests. So for all of the t's here, okay, we're going to do t. We're going to replace it with number, all big. Not that t. No. No. Yes. No, no, yes. Oops. Yes. No, no. No, yes. No, no. Oop. Dang. Well, I saved some time there, maybe. So I'm going to say bool be success equals this. And I'm going to say that equals this, and that, and okay. Standard cout bool output, and we're going to do b success inline. Okay, so if all these are true, then it's not ill-formed. Right? Turn 0 here. Just to make that really clear. Yeah, true. So every single one of these things is true. It's trivially copyable, it's copy constructible, it's move constructible, it's copy assignable, and it's move assignable. So, what the heck, seriously? It even shows a structure, just like I'm doing. Standard atomic counters count. Specialization for the user-defined type. Atomic bool uses the primary template, is guaranteed to be a standard layout struct, has a trivial destructor. Partial specializations. Anyway, I'm not going to get too much far into this, but clearly this didn't work. So I feel like it's a bug in the compiler, but I'm having the same exact behavior with CL.exe from Microsoft Visual Studio. So I don't know. Maybe someone in the comments can chime in. Now, if I had done this though, if I had said standard atomic int, and I had just messed with the structure directly, let's try that real quick. I'm going to say in.x++. Okay, we're going to do the same thing over here. Actually, wait a minute. Comment all those out for a second. I'm just going to say number in. Okay, yeah. We'll comment both these out for a second. Okay, just in.x. And that does work. So you can have a class or a structure full of a bunch of atomics, and that'll work just fine. And that's actually what I'd recommend if you have primitive types like that, and they're just like one-off things you need to be thread safe. But typically, if you have like a greater class object or something that needs to be thread safe, I would use mutex. But this is a cool option for small scale stuff. But I kind of want to... Do I really want to get stuck on this right now? You really shouldn't be doing this way anyway. This is kind of a dumb way to do it, making the entire structure atomic. Okay. So this didn't work, even though it should be atomic when I try to grab the entire number structure. And I modify value from within that structure, and I atomically store that modified structure. Let's get rid of this again. And then, yeah. That's really interesting to me. I would expect that to work. Because the thing that you're actually modifying is the type you put in here. And the type I'm putting in here is the structure. So as long as I modify the whole structure at once, it should be thread safe. And this does satisfy the trivially copyable thing. And just to show the trivially copyable thing, I can do this. I'll say like, I don't know, void operator operator equals. And I'll say int RHS or something, or maybe, I don't know, const number reference RHS. And I say x equals RHS.x. That actually won't compile. It's going to say it's not trivially copyable. Right here. So instantiation of struct standard atomic number required from here. Error, static assertion failed. Standard atomic requires trivially copyable type. Static assert is trivially copyable. False evaluates to false. So that is how it's defined in the standard. It has to be trivially copyable, and this is trivially copyable, and I am modifying the whole structure at once, so I don't know why that's not working properly. In fact, I kind of want to, out of curiosity here, developer console. What if I do this in Visual C? And I say something like go to D, that should just be here, and then it's going to be code, tepid coder, and then it's going to be, what do I call this? Keywords, right? Yeah. Okay. CLS, and we're going to do CL.exe. It's going to be test.cp, out is test. Okay, let's do this. It should compile it. So, warning. Exception handlers used, but on one semantics not. Yeah, whatever. It's talking about exceptions. Okay. It's really hard to read this. See reference to class template. Basic OStream being compiled. OStream something other. First reference, okay. Looks like it made it. Output is test.exe, so let's say test. Same problem. That is bizarre. Huh. So, I can't blame GCC for this, as much as I'd like to. But that should be an atomic operation. It's thread safe on a trivially copyable object, which is just, it happens to be a structure. What am I referencing here? I'm referencing N, which is the structure that's atomically defined. And here I atomically set it to 0. If I do this, into equals in, and I say standard cout, I'm going to say initial in value we just pulled out is going to be into dot x. Okay. Okay, compile it first. Yeah, it is starting at 0 like I told it to. That's good. What the heck? Temp is in, which should have it atomically. I increment the value, and I put it back in. This is going to be all kinds of clobbered output, but jeez. Oh, you can see it jumping all around there. Look at that. That's because sometimes the numbers are being, what do I say? Printed out before the line break of another number is printed out. And there are 2 line breaks happen at the same time. Because they're all fighting to put output into centered out. Yeah, 5, 6, 7, 8, 9, 0, 1, 2, 3. Those are all good so far. 3, 2, 1, 0, 9, 8, 7, 6, 5, 4. 3, 2, 1, 0, 9, 8, 7, 6, 5, 3. 0, 5, 7, 6. These are mostly looking good here. Of course, the C out might have synchronized them a little bit. Because they all take longer to do what they're doing. Five, 4, 3. Here's a 0, then, yeah. 0, 1, 2, 3, 5 digits. 1, 2, 3, 4, 5 digits. So you have, should be this right here. So we got a 4, and then we have, interesting. Might be 3 different things collaborating at once here. It's weird that somewhere in 24,000 is other than 30s. 50s. That is kind of bizarre to me. Yeah, I don't know. I'm just gonna say don't use this for anything but primitives. Prefer a mutex if it's something greater than a single variable, like a single int, single float, single double. But I feel like this is a bug, unless I'm misunderstanding something about the standard here. I mean, when I read the spec, it's saying that atomics are limited to trivially copyable classes that have no custom copy constructor, and whose members are also trivially copyable. So, anyway, I'm not going to get stuck on this. Let's move on to the next topic. And the next topic is going to be a different keyword. So I'm going to say, let's call it test2scb. Doesn't really matter, I'm not going to compile this one. Let's say I have just some function. Alright. Inside the function, I'm taking something like a reference to, let's say, IRA, pointer, buffer. I'm going to say I have size t element count. How many elements are in that buffer? Now imagine I have a variable, a, and I say it equals IRA buffer. So it's basically IRA buffer 0, right? I'm pulling the first element out. And I say something like a plus equals 17, and I say something like IRA buffer equals a, right? So I've basically said read from the first element of this pointer to an array of integers, store it in the variable a, add 17 to it, and then back in that same position, offset 0 in that buffer, store the value a, which is 17 higher than it was. And I could do something over here and say int b equals IRA buffer, say it's 1, so the second element. And I'm going to say b minus equals 2, I'm going to say IRA buffer position 1 now equals b. Alright, what can happen is the compiler can actually reorder what I've done here. Because you can imagine there is something in memory, a contiguous block of integers. Let's just say the integers have like the values equal to their index. So I'm going to say 0, 1, 2, dot to dot, and we'll say n minus 1 is the last element, right? This would be the first element, this would be the nth element. Okay, so what happens is when a read happens in memory, usually you'll pull a bunch of stuff into cache, and you can work with that cache line and do a bunch of operations with it at once. So since each read is expensive, you kind of hope that other data you need is also near that thing you grabbed. So if I'm grabbing the first element here of this array, grabbing this, I'm probably getting a pretty big cache line full of stuff, just in case I need other stuff in that area. And it ends up being faster a lot of the time, because a lot of times you are reading things like structures, which have a bunch of members that are close together. Sometimes you're reading from a bunch of variables in a function. Like this B and this A are probably contiguous in the stack if I print out their addresses. So that means if I'm grabbing the, memory around A, it's very likely I'm also going to get the memory around B, which is going to be faster than having to ask for this memory, wait for it to come back, do something with it, then ask for this memory, wait for it to come back, and do something with it. So what's probably going to happen is, what I've written here is going to get reordered. The compiler's going to say it'd be faster, if I did all these reads, which are close to each other, at the same time, and do all the writes, which are close to each other, at the same time, right? And if these values are small enough, like these are just characters, each character I'm going to just say is a byte each for all intents and purposes. There might be some platforms where a character has like, I don't know, 15 bits or something weird, but maybe I shouldn't have used character example. Let's say I have an unsigned 8-bit integer or something. Okay, if I have 2 of those, I can fit that in less than the size of one int, right? So if I'm in a 64-bit architecture right now, my registers are going to be like RAX, RBX, whatever. Each of these are 8-byte registers, right? I have 8-byte registers. That means when I write to memory, it kind of wants to write and read 8 bytes at a time. So if I only have 2 bytes of stuff to set in here, it can do it all in one operation, which is really fast. So this right here, if these variables were small enough, could just be one write operation. And this right here could just be one read operation. I could be shifting things and handing them out from the one thing I read in order to get these values into the stack locations I need. It is entirely possible that these things may never actually even touch the stack. It could be that this gets read into a register, some operation is performed, and then it writes it back out from that same register without actually even touching this variable in the first place, right? And you can imagine, I could write that in C++ in a way that makes sense, like IRA buffer plus equals 17, right? Here you're not even seeing a local variable. So I mean, it might be something like this that you see. It might be like RAX equals, keyword, PTR, whatever, some address, IRA buffer, right? So I'm actually getting a keyword from that. Keyword being 8 bytes, a D word being 4, word being 2, and a byte being 1 byte. Anyway, you could imagine that happening in add REX, comma 17, would be something like, this would be a move, by the way. Move it to that. If you move the value at IRA buffer to the value at RAX. And really, I mean, it would be something more like, let's say I have move RCX to keyword PTR IRA buffer. Like, it's just basically the location memory of this. I don't need to put the keyword there. I haven't done this in a while, so bear with me. But essentially, I think it would be this. You basically move this to the address stored here, like it's something on the stack. And I'm saying move RAX to the value stored at that address in RCX. I can't actually use this stack location directly. I have to put it in a register. So this has the address right here. And I'm saying dereference this address to get the value at that address. I'm adding 17 to it. And then again right here, I'd have to say RCX, I think. And say modify the value at that address right here, the first value in this integer array, to be equal to whatever RAX is, which is 17. Well, 17 plus whatever I pulled out of the memory address. Anyway, that's probably what's happening here. I don't think it's actually going to move this into any stack variables. The important bit is just that if you do all the reads at once, it's possible it's all going to be in the same cache line, and it can do one read instead of a bunch of reads in the CPU, and the compiler's trying to plan for that and make it faster. So if we can do one read and get both these values, great, and then we can do the operations all at once because that doesn't require any reading or writing really. It just happens to the registers. Okay, and then the writes all happening at once is good because the writes small happen at once. Now sometimes there's a problem with compiler optimizations, and I want to show an example of that. So I'm going to come up with a bit of a contrived example here of when this might be useful. Let's say I have some reading that I'm getting from a sensor. So start polling I reading. Now it's possible that we're on some kind of platform that doesn't have multiple threads of execution, and so we're not able to do any kind of like locking mutex to guarantee that the value we have is not updated while we're using it. So that could be a problem. It could be that we're also using some kind of like memory mapped file, so that we're sharing memory with a different process. And I mean, there are ways to synchronize two different programs to work with one another, such that they don't clobber each other's memory while one's trying to actually work with the data. Like do a copy. You don't want to write while someone else is copying, and you don't want to copy while someone else is writing. So anyway, let's just imagine that, for the sake of argument, there's a sensor we're reading from, and we have no control over when the update happens, right? So what you might say in this case is like you have int x equals I reading plus 2 or something, and then int y equals I reading, let's say divided by 2 minus 7. Whatever. It's entirely possible that the reading it gets, since this might have updated between these two lines, is going to be different. But it's also possible the compiler says, you know what, this programmer seems to like reading a lot because they're referencing this variable multiple times. Let's just keep that in a register so it's, you know, quick to access. If we take it to a register and have to read again, that's slow. You can imagine the processor is usually measured in gigahertz for its speed, which is billions of operations per second, whereas the RAM is usually measured in, or every case I've seen, it's measured in megahertz, which is millions of operations per second. So there's a big discrepancy there, right? It's an order of magnitude of difference in how fast it can operate if it has to read from memory. So if we can keep something registered, it's actually a good thing in most cases. But if for some reason that we need to always use the newest reading for independent operations on this reading, then what we can do is we can say we want a volatile int, and that means it has to read from memory every single time. It also means it can't try to optimize stuff out that uses this variable. So it's pretty useful for situations like that. Now, if something's written in here like float f equals 99 or 88, whatever, f, this won't be affected. This could be reordered still, because this doesn't actually include that variable. But anything that's acting upon that variable, or something that, like, let's say it equals 99f plus float x, now it probably can't be reordered, because this touches the x, and the x touches the reading, right? So anyway, that's a nice thing to know, especially if you're trying to benchmark something and you're wanting to remove compiler optimizations to see how fast some arbitrary operation is. Anyway, there's kind of a vague situation where it might matter, but I can also show an example of how the compiler might reorder things, just in general. Let's say I have int x equals 0, and I have for, I'm going to say int I equals 0, I less than 10, I plus plus, and inside the loop you say x plus equals 2. Well, the compiler could detect that, hey, it's going to run 10 times, it starts out at 0, and it's going to be 2. That's the same thing as saying x equals 10 times 2, right? So all of this code would just get optimized out. And it's going to know that 10 times 2 is 20, so it's just going to assign x to 20, right? The compiler can do that because of the as-if rule. And this volatile should prevent the compiler from doing that, or it should at least be a hint to the compiler that you don't want that to happen. Okay, and there's other cases too where things might be optimized. Okay, so say you have a function called, I don't know, get num. Alright, and you have like int a, and you have bool b add, let's say. Okay, now say you have something like int x equals a plus 2. Alright, and you have something like if b add, you're going to do something like x plus equals another 2. Else, we're going to say x minus equals 2, right? We're going to subtract otherwise. And you'd say return x. Well, okay, in this case, what do we really have? What we'd have is a plus 2 minus 2, which is just return x, right? You can optimize that out. The compiler probably see that and optimize it. Over here, we have plus 2 plus 2, so it's return x plus 4, right? So we've already optimized that quite a bit. But we can actually do better than that, right? The compiler could say, well, realistically, if this is true, we're passing x plus 4. If it's false, we're passing just a, right? Well, then what we could do is say return a plus b add question mark 4 0, right? That's the same thing. If that's true, we're adding 4. If not, we're adding 0 to it. All right, so either returning a or returning a plus 4. But we could say, if we treat add like an integer, right, we could say int add times 4. Because now, what it's going to say is, if it's true, this will be 1. If it's false, it'll be 0. So 1 times 4 is 4, so we're adding 4 if it's true. Now, if it's false, it's going to be 0. 0 times 4 is 0, so a plus 0. So that'll do the same thing. That's the kind of thing the compiler will do. But you might want to be, I don't know, trying to think of a case where this would matter, but you might be benchmarking something and you want to see how it works without any optimizations. So instead of letting the compiler do that, you might mark a in this case as being volatile. I'll write the old version of the function again real quick. So get num a bool b add. I'm going to say if b add, okay, else we'll say a minus equals 2, this was a plus equals 2, and this was, and, oh, not a, sorry, x equals a plus 2 to start with. Right, and returned x. Okay, so what you could do then is just mark this volatile, and it should be a hint to the compiler that you want this to be in here. We don't want to optimize it into this. So, what did I cover so far? We covered standard atomic T, which should work for all trivially copyable types. I suggest using it only for integral and floating point types. And I'll be, should I be more explicit than that? No. When I say integral type, I'm also including things like char and w char t and, like, I don't know, char 32t, whatever. I'm including those too. I'm including these types. In fact, I'm including types like these, to be very clear. Okay, I also talked about volatile. Now, in a follow-up video I want to talk about some different keywords as well. But I'm going to leave that for the next one. If you like this video, give it a thumbs up. Consider subscribing for more content like this. If you have any comments, suggestions, criticisms, I'd love to hear those. Especially if it's about the whole atomic thing when I had an atomic structure that was trivially copyable, but still gave me a race condition. That is a bit strange to me. I feel like it should be a compiler bug unless I'm misreading the spec, but anyway, I'm going to leave it at that. I will catch you guys next one. Thanks for watching. Have a good day.